Suddenly my backslash. Only one. Maybe the first few minutes will be Alright, let's start. So today we'll continue what we started last time. Start discussing probabilistic algorithms. We're going to talk about this notion of an expected running time, which we kind of hinted at last time. Okay, so as all of you know, so midterm grades are out. I didn't bring the answer sheets today, but you can come by to my office hours or follow me after the lecture and you can get them if, in case you haven't collected. Most people seem to select it. Right, and so many of you were, after the midterm grades, I guess, concerned about the grading of the course, how I was graded and so on. So, I mean, I wanted to emphasize that for grad courses, usually we don't follow this above a certain threshold is A, above like 85 to 90 is A minus, something like this. Usually we just, we look at the scores and try to give something like, you know, the top 15% get an A, next 15% get an A minus, something like that. So it's mostly how you're doing relative to the class that matters, and we try not to be too harsh. Okay, so that's generally true for grad courses. So if you have generally concerns about how you are doing, feel free to come and talk to us. Okay? And also, I forgot to mention here, there's a midterm course survey, which all of you should fill out. You don't have to, but it's nice if you want to give some feedback. Okay, so it's and yes, it is. If you want to fill it out anonymously, you can just do it in incognito mode or something. Okay, so it's totally fine. Although I will not really look at anything beyond the statistics. Okay, so feel free to do whichever way you want. And do it only once. Don't do it. I think in principle you can do it multiple times, but it's good for you if I get a good signal. Okay. So, all right. So that's the midterm course survey. All right. So yeah, and I think at least 12 or so people already answered. So thanks for doing that. So anyway, so this is what we started looking at last time. So we started with the general high-level question of can tossing coins or can randomness help in algorithm design, and we saw a bunch of examples. So one example was if you had an array that was unsorted and you knew for a fact that some element was occurring lots of times, something like n by 3 times, can you actually find something like that and one such element? And we said that you can, but just by checking elements at random. Okay. And so the next thing we tested was this question of you're given two polynomials that you can actually evaluate efficiently, and you want to know if these two polynomials are identically equal. And here we said that just checking the values at random points is actually a pretty good test, and I said that this has applications to like circuit design and so on. So, and the reason this is not true is because a priori it's not clear that if polynomials agree at random points, then they have to be identically equal, right? Like you could just by accident agree at a lot of points. Okay. So, but yeah, what we know is that that cannot happen. And we also had another application, which was we had a graph problem where we said that if you had a bipartite graph, you wanted to check if it had a perfect matching. So this was a little bit more involved. So we said that you could write out a polynomial. Actually, I forgot to give the name. It's called the Dutch polynomial. So you could write out a determinant. See, the Dutch polynomial is the component, but it's something related to this. So it is, so you could write out a matrix whose determinant was a polynomial, and it would be identically 0 if the graph did not have a perfect matching, and it would be non-zero if it did have a perfect matching. So you can use something over here to check if a bipartite graph has a perfect matching. So this is a slightly non-trivial example, but I wanted to just illustrate to you that sometimes you can do some non-trivial things with randomness. Okay. Alright, so but the flavor of all of these results is what I call finding hay in a haystack, right? So in some sense, something was occurring lots of times, and you just had to find it. So and that's where randomness is very useful, right? Because intuitively, if most of the things are guaranteed to work, if you pick something at random, it's pretty likely going to work. Okay, and that was the analysis for all three of these situations. And in all of these three applications, at least the ones we saw, there was some probability that the algorithm failed. And there was this trade-off between the success probability and the running time. Okay. So we said that even in this very simple example, if we run for time r, then success probability it was roughly something like 1 minus 2/3 to the r. So the failure probability is exponentially small, but there is still some some probability of failure, non-zero probability. Okay. So this I said is common. And then I also said that there are these other classes of algorithms which we call the Las Vegas algorithm. So these don't have any failure, okay, so they always work, but the running time can be large with some probability. Okay, so they are never incorrect, but the running time could be large. So actually we'll see an example of this in this class. And these kind of algorithms are obviously preferable because they never make a mistake. It's just that sometimes they can be slow. Okay? Yeah.
So for the Las Vegas algorithm, can we say that the running time is always better than deterministic approach?
We would like algorithms which have that property. Okay, so yeah, so what we would like, so his question was, would it be true that if we look at a Las Vegas algorithm, the running time would always be better than a corresponding deterministic algorithm, right? And that may or may not be true. Okay, but we would like algorithms where using randomness you only get an improvement. Sometimes you can get a drastic improvement, but sometimes maybe it's not so much. Okay, so that would be the ideal kind.
But in some cases, it can be much worse than.
Oh yeah, so for typical algorithms, sometimes it could be worse than. Maybe it would be much worse. Actually, we will see quicksort where sometimes it can be significantly worse than merge sorting. But yeah. All right. Okay, so what is today's plan? So today is all going to be about expected running times and expectations of random variables. Okay, so you should put on your probability hat now. Okay, so let's start here. So let's start with very basic question. So if you have a random variable x, what is the expected value? Okay, so the expected value, this is the basic definition. So a random variable is, it has some probability density function. That is, if your random variable is x, then given any point, there is some, it has some probability distribution. Need not look so clean, but it can be something like this. So it's something like this, and the probability that it is between these two values is given by this area. It's the standard definition, right? So it's so this function is called the PDF, or the probability density function. Okay, and I'm denoting this by P of. All right. So given this definition, so what is the expectation? The expected value is defined to be integral over the whole range. So this is for a real valued function. So this is a random variable that takes real values. Okay. Then you have expectation over the whole interval of x times p of x dx. The x wasn't there. What do you get? You get 1, because the integral of just the density function would just be probability everywhere, the total probability, which is exactly 1. And so you are weighting that by x. Okay, so that's what goes on in expectation. Alright, so this is standard definition. So now, alright, so just to give a sense, I thought I would throw in a few examples. Maybe I won't go too much into them, but yeah, so if you had something like, you had a distribution which is uniform in 0, 1 and 0 everywhere else. It's like saying P is 0 here, and then over 0, 1 it is uniform, and then it is 0 again. So if it's something like this, then the expected value of this, if you just, so expected value, what would the expected value be? 1. So I said it's uniform.
I mean, the integral of that function is 1.
Sure, I mean, integral of p of x is 1.
1 by 2.
Yeah, so it's integral is the average value, right? The average value is half, because if you're uniform in 0, 1, then the average value is half. Okay, so but you can do it computationally, right? So this p of x is in this case it's 1 if x is in 0, 1, 0 otherwise. So now if you do this integral, it will just be integral 0 to 1. The minus infinity to infinity will just become 0, 1, because anywhere outside the interval p is 0. So you just have this times x dx, and this is something like x squared. The integral of this is x squared by 2, and subtract to the usual stuff, you get half. Alright, but also intuitively it should be clear, because you are symmetric in the interval, symmetric about half, right? So the expected value. And the same with the Gaussian. So the Gaussian is, hopefully it's a distribution that all of you have seen. If not, you will encounter it in many courses. Okay, so it's a distribution where the P of x looks rather complicated. P of x is something like 1 by e to the minus x squared. Yeah, it looks complicated, but it has very nice properties. Okay, but the point is that this is the density function only depends on x squared, so it's symmetric about 0. Okay, so and because it's symmetric about 0, you can easily show that if you compute this expectation, the x part and the minus x part cancel out, and the expectation becomes 0. Okay, so the expectation is 0. And likewise, alright, I want to throw in one discrete random variable. So the definition I have here is in terms of an integral, which means it's like a continuous variable. But you can very well define expectations for discrete random variables as well. So in this case, it would just be the sum over all the choices of sum over all the elements. So this would become something like sum over all x times probability that capital X equal to. So this would be like the discrete analog. Right? So you can use this definition to say that if I have a random variable that is Bernoulli, it's 1 with probability, let's say 1/3, and 0 probability 2/3. So the expected value is it's 2/3 times 0 plus 1/3 times 1. So these are all obvious things. I just wanted to recap the definition and do a couple of examples. Okay. So this is the general definition of an expectation. Okay. Any comments? Any alternate things that you've seen that you want? All right. Good. So this is the expected value. So why do we care about the expected value? So the point is that we want to look at the expected running time of algorithms, right? So the x, which is the random variable we care about, will be the running time of certain algorithms. Okay. So that's the context we're interested in. So let's recall the problem from last class. Okay, so you are given an array, and you know that 1/3 of the so it must be n by 3 of the ai are 0, and your goal is to find one I such that a of I is 0. Right? So this was the problem that we discussed. You are given some unsorted array A. Okay, and you are guaranteed that n by 3 of the ai are equal to 0. Your goal was to find one index I such that a of I is 0. And we considered this Las Vegas algorithm, right, which basically said, while not found, pick a random index I and check if a of I equals 0. So this can potentially go on forever, as we discussed. And okay. So let's consider this very simple algorithm and find out what its expected running time is. Okay. So how do you now compute? The hint I gave is that last time this is similar to tossing a coin until you see heads, right? So very similar to that. But let's formally do this analysis. So by definition, right? So let's define x to be, this is a random variable, which is the running time of the algorithm. Okay. And if you wanted to go by definition, so the expected value of x is just sum over x going, little x going from 1 to infinity of probability that, sorry, x times probability that capital X equals 1. So this is just the definition of the expected value, right? Now, so this is fine, this is just whatever x is. So what is the value that, what is the probability that the running time of the algorithm is exactly equal to x? Sorry?
3%? 1 divided by 3?
Well, when x is 1, yes. What about for general x? Yeah, so this will exactly be a geometric distribution. So when is the running time exactly equal to x? Right? So it means that in the previous x minus 1 iterations you should have failed, and in the x step you should have succeeded. Correct? So that's when the running time will be exactly equal to x. Okay, so you can write this. So this value is 2/3 to the x minus 1 times 1/3. Okay, so that's what you can write down. So you should have failed all the previous times. You should have succeeded at time x. Okay, so that's when the running time would be exactly x. Alright, and now you can evaluate this, right? So this would be exactly equal to, of x times 1/3. And yeah, so I won't show you how to simplify this. There's a lot of ways because we'll see a slightly nicer way of doing the same thing. So if you simplify this, you end up getting exactly, what do you end up getting? Any guesses? Yeah, if it's like Bernoulli P, you would get 1 by P. Somebody said 1 by P. So what is P in this case?
1 divided by
Yeah, so I mean, intuitively, it's like I have a coin and I see heads with probability 1/3, right? Like heads is like succeeding. And I'm asking how many times should I toss it in expectation to actually see heads? Okay, so it's worthwhile doing the computation for you guys then. So you should do it once you're back at home. And you will end up showing that this would be exactly 3. Okay? Like if you had a coin which has a probability P of coming up heads each time, the expected number of times you got to toss in order to see heads is 1 by P. Okay, so that's it's a believable fact because if P is tiny, you need to toss more times. Otherwise, you have to toss less. So this turns out to be exactly 3. Okay, so this is So it's actually part of homework 0, but you should do it in case you haven't. Okay. Alright, so that's some basic definition of, so here we just plugged in the running time, the definition of the expectation. Now it turns out that doing this for most algorithms is very difficult. Okay, like suppose you have Quicksort, and I ask you what is the probability that the running time is like 4n plus 5. Okay, so this is you can imagine this is a very tricky question to ask. Okay, so we come up with a slightly different way of doing this, and these are what I would call the recurrence for the expectation. Okay, so it's kind of like you write out a recurrence, but you write out a recurrence for the expected value instead of the actual running time. Okay, so we'll see that in a few examples. So let's start with the toy problem. Okay, which is exactly what we were considering earlier. It is what is the expected number of the process of a fair coin before seeing heads. So fair coin means it's half, there's a half probability of it. And what I just told you, the answer would be 2, right? Because there's a probability of half of it. So 1 by p would be exactly 2. But let's see a slightly, and I told you that if you do a computation of this kind, you're going to end up with a value. Okay, but let's see a slightly more interesting way of doing it. And so the idea is to use some inequality of this kind. Okay, so this is an identity that holds for any random variable x and for any event f. So what you can say is that the expected value of x, you could also write it as probability of f times the expected value of x conditioned on f occurring. Okay, so f can be any event. Okay, and so you compute. This is called the conditional expectation. Is you will see intuitively what that means in a few examples, but there's also a much more formal definition. Times the probability that f does not happen, which is 1 minus p of f, times the expected value of x conditioned on f not happening. Okay, that's what I mean by f bar. Okay. So I think this has a name, but maybe it's called the law of conditional expectation, something like that. So this is called the conditional expectation. So how many of you have not seen something like this before? Actually, how many of you have seen this before? Almost a few. Okay. So this is a standard trick people use to compute expectations, but it's actually, and the proof of this is basically by Bayes' rule. Okay, by Bayes' rule, you just expand it out and you get what you want. Okay. So let me not go into that. In fact, once I plug it into the to deduce that, you will immediately, this will sound familiar. Okay, so let's say I want to use, actually any questions about the statement, because I think this notion of conditioning on any event may be something that's a bit tricky to people. Yeah, just pause for a little while you process. And so the important thing is here is that here there is an f and there is an f bar, which means the complement of f, that is f not occurring. Yeah.
Is the event being held for the point?
So f can be anything. Okay, so f could be something along. It could be as simple as, oh, is the first coin held, or it could be something like, are there some odd number of coins in the first 100 tosses, something like that. Okay, so f could be any event of your choice. Okay. So but it should be a well-defined event in the sense that it cannot be something totally.
Why are we using f at all?
No. Here I just stated this result for any f. We'll see what f to plug in to get some nice result. Okay. We'll see how this view of the expectation gives us a clever way of finding that expected number. Okay. All right. So without dwelling on it too much, so let me now show how it's used, and then you can appreciate this definition. Right? So which will answer his question. Okay. So let's say I denote the expected value of this by some value, let's call it alpha. Okay, so this is the expected number of heads, this is the value, let's call it alpha. Right, again I needed to have written before seeing this. Right? So let's call the expected value alpha. And now I'm going to define f to be the event which is the first, or rather is the outcome Okay, so F is the event. I wrote it as a question, but if you want, you can think of it as F is the event that the outcome of the first toss is equal to heads. So F will is said to occur if the first toss results in heads. Otherwise, F bar. Okay. That's how I'm defining it. All right. So suppose I define F that way, then what is expected value of this X, which is our number of times you have to toss, conditioned on F? 1. Yeah, so this is exactly 1 because F was the event that the first toss was the head. Okay, so conditioned on that, X has to be 1 because the first step will always succeed. Okay, so in this case, so the expected value of this X conditioned on F equals 1. Now, what is the expected value of X conditioned on not F? Okay. So not F just means that the first toss was a tail, right? So if the first toss was tails, then what can you say about the expected value of X conditioned on that event? Can you relate it to the alpha? Yeah. Right. So what are we asking? So this is like saying, what is the expected number of tosses to see as condition on first toss equals state. Okay. In some sense, we are conditioning on the event that we lost one chance. Right? We lost the first try. So what do you think is this value in terms of alpha? Can you, yeah.
So it's going to just go back to the expected value of X because throwing a tails does not affect anything.
Exactly. So the process is all history independent, right? So if you threw a tails the first time, so then you have wasted one chance, but modulo that, you are in the exact same situation as you were at before the toss of the first coin, right? But you have an extra 1 because you have to because you lost the first chance. Okay? So this value turns out to be exactly 1 plus alpha, which is the expected value of X. Okay, because you've lost a chance and then you have arrived at exactly the same place where you were at before the toss of the first coin. Okay, so what you have is that the expected value of X given this thing is something like 1 plus alpha, is exactly 1 plus alpha. And now you have quote unquote recurrence here, right? Which is that you can use this expression. Okay. Say that alpha is equal to, so the probability that F happens, what is the probability that F happens? Yeah, so this is exactly half because it's a fair coin and it's the event that the first toss is heads. Right? So first toss is heads with probability half. So it's half times 1 plus half times 1 plus alpha. Okay, and if you simplify this, you just get alpha equals. Okay. So note that you're not summing any geometric series, you're not doing anything computationally intensive. Right? So you are just you're just using this reasoning that you are in exactly the same position as before, just that you lost one channel. And I'm calling it a recurrence because you are expressing alpha as something that, in some sense, also depends on. Right. So, any questions on this? Yeah. Oh, sorry.
Could you really please go through that simplification?
Which one?
Like the last one, because I'm getting 2/3 for alpha.
Oh, okay, so that is the easy question. Okay, so here it's, so this one just simplifies to alpha equals 1 plus alpha by 2, okay? Because the half here and the half here adds up to 1. And you get alpha equals 1 plus alpha by 2. And then, so this is like, take the alpha by 2 here, you get alpha by 2 equals 1, or alpha equals 2. Okay. That's fine. Just have to do it twice. Yeah. Yeah, so the main tricky thing here is that we concluded this fact, right? Like the probability that x conditioned on the first toss being tails is actually 1 plus alpha. Right? And the reasoning for that is that the process of tossing coins independently is entirely history independent. Right? The fact that the first coin came up tails does not affect whatever happens in the rest of the process. Okay? So if I tell you that the first coin came up tails, and I ask you to find the expectation of the number of times you have to go in order to see heads conditioned on this fact, then it would be exactly 1 plus whatever the process would be if you had started at the second toss. Right? And starting at the second toss is no different than starting at the first toss if you had no information. So that's the reason, and that we defined to be alpha. Right? So the definition of alpha was exactly the expected number of tosses of a coin in order to see heads. To see the first. So that's the reason you have something of this kind. Yeah.
So whenever it comes to finding zeros in an array with a third of zeros, it's also going to be history independent. Is that correct?
The algorithm that we defined it, yes. Yeah, because I'm just independently choosing an index, and yeah. Yeah. So the expected running time of this algorithm, even though the worst case running time can be infinite, right? But the expected running time is just a constant. All right. So okay. So this was a very simple example where you came up with, in some sense, a recurrence for the expected value. Okay. So let's now see a more interesting example where you can come up with a recurrence for the expected value of the right. Okay. So, and the example we'll see is Quicksort, which many of you hopefully would have seen, and but I'll just recap the algorithm anyway. Okay, and the goal is, of course, to sort some unsorted array A. Okay, so you're given an array with n elements. Your goal is to sort it. And so the algorithm is very simple. You pick some element of A uniformly at random. Okay, and call that the pivot. Okay, and now you partition into two subarrays, B and C. Okay, so B consists of let's call this some A of I. So that's a pivot. B consists of all elements of A that are less than or equal to A of I. And C consists of A that are you know, just to avoid some cases, let's write it as more than. So that both these arrays are always strictly smaller than the original array. And then you recursively sort B and C, okay? And then you concatenate the answers, which is you write down the sorted B, and then you write down E of I, and then you write down sorted C. And this will then be the whole sorted array. And the point is that this would work for any A of I. Right? You could have done this with any A of I. Form an array B which is everything less than that, and form an array B which is everything C which is everything more than that. And then you sort B recursively, and you put this element, and you put C, and you would have gotten a great solution. I mean you would get a valid solution. But the only trick we are throwing in is we want to pick a random element of A as this pivot. Okay. So no matter what this random choice was, the algorithm is always guaranteed to be correct. Okay, that's the point I would like to make. So sometimes in randomized algorithms, the algorithm will only be correct with a certain probability. Here, correctness is not an issue. It's always correct, always returns the right answer. That's why it's more of a Las Vegas style algorithm. Okay, it always returns the right answer. The running time depends on whether we were unlucky or not, okay, as we will see. So is the algorithm clear to everyone? So this is the most common sorting algorithm that people use. So like Unix sort and things like this use it. So yeah, if you don't know it, you should understand this. Make sure you understand. Oh, recursively use the same procedure. Yeah. Whenever I say recursively use, I just mean use the same procedure. There will be some obvious base case, like an array has one element. Yeah. Okay. All right. So this is a procedure. Now let's look at the worst case, right? So how long could it take? Could it potentially take n squared time? I see few nods. So when could it take roughly n squared time? One of them is empty also. Yeah, so you could end up with a situation, maybe that's what you would say. Yeah. Okay. So you could end up with a situation where maybe you pick the largest element. Okay. You were very unlucky, and of all the elements you picked the largest one. Okay. In which case what could happen? Okay, so now B consists of everything apart from that element. So B is now an n-1 element set, and C is empty, and you end up with a recursive problem of size n-1. Okay, and so you end up with some recurrence of the kind T of n is like T of n-1 plus n, and then yeah, so this one next time maybe you're unlucky again, let's say, and then you get T of n-2 plus n, whatever, so something. Something like that. But if you think about it, what's the probability that something like that happens? Right, so what is the probability that the split at the first level was that unlucky? Like you ended up picking the largest, or the same thing will happen if you picked the smallest. But what is the probability that you pick like these two endpoints of all the lot? 2. Yeah, so the probability that this happens is something like, probability is like 2 by n, because you have to pick one of these extreme elements. And this is tiny, right? If n is large, 2 by n is very small. Okay. So you don't expect something like this to typically happen. So, and that gives us hope that maybe things won't be as bad. So, all right. So, and you can actually carry forth this analysis, and you can say that the probability that it takes n squared times is actually exponentially small in n. It's a nice exercise if we were to do it if you haven't seen it before. But so you can show that it's pretty tiny that that the probability is something like n squared. Okay. All right. So that's fine, right? But now the question is, what is the expected running time? So this is a clear randomized procedure, and we can ask what is the expected running time on an array of length n. This is a valid question. And now you can see, right, if I want to do it by the definition of the expectation, this can be very tricky, right? Because what is the probability that I run for exactly, 20n steps, right? So then you have to think, oh, okay, this recursion should go down exactly 20n or something like that. That would be extremely messy to think about. Okay. So we're going to use what we did earlier. We're going to come up with a recurrence for the expectation. Okay, so actually one other thing I wanted to mention before going there is this notion of, okay, I told you what a bad pivot is, which is if you pick one of the extremes, then you're in bad shape, right? Then you get a problem of size n minus 1. What would be a case where you expect that the running time would be nice? Yeah. Yeah, so if you choose somewhere in the middle, you expect that the problem would be much nicer, right? Like, in fact, if you were to choose always the middle element, right? Let's say, if you're very lucky and you always choose the middle element, then you expect something like, you expect recurrence of the kind t of n is t of n by 2 plus, because you recurse on n by 2 size problems, and you get plus n. And this is exactly the recurrence we had for merge sort, if you remember. Okay, so this is precisely the recurrence for merge sort. And so this is a good case. So you get n log n as so you know that this solves to something like c times n log n. Okay. But you might say, okay, this is also a very lucky case, right? What is the likelihood that you pick exactly middle element? That's also 1 by n. Right? But the point is that suppose you picked anywhere somewhere in the middle, right? So somewhere between n by 3 and 2n by 3. So this is now a pretty reasonable probability, right? With probability 1/3, you can expect to get lucky this way. And now you are in okay shape. So now, even here, even in this extreme, you get a recurrence of the kind t of n is t of n by 3 plus t of 2n by 3 plus n. If you always split like this. And so for those of you who are comfortable with Akrabas and so on, you can actually check, or you can do just guess and verify or something like that, that this solves to also exactly Cn log n. Your favorite theorem of these two adding up to n. So that's the other. So this also ends up solving to c times n log n. Okay. So this gives us hope, right? Because with a reasonable probability, you would be in a situation like this. So this is a reasonably good split, and even here you are having a recurrence that solves to c n log n. Okay. So, all right. So let's now try to write out an expression now formally. So, okay, and so for this I'll define some notation. So let's define f of n to be the expected running time of Quicksort on an array of length. Okay, so this is how I'm defining this. So it's the expected time array of length. Yeah.
There was a line on the previous slide that said it suffices to encounter log n good words. Could you explain that?
Yeah. So, okay. So what I wanted to say was that, okay, so if you encounter a good pivot, which I didn't formally define because I thought that this was not maybe so important, which is something that lies between n by 3 and 2n by 3, then if you define that as a good pivot, then in some sense, if you encounter roughly log n good pivots, then each time the array size would split by a factor of 2/3. So if you do that log n times, you end up with an array of a size constant size. That's all I meant. But then I realized that it's not that crucial to emphasize it. So I tried. Yeah. Well, that's a good get. Yeah, some of these slides are also last year's slides, so things will remain, and yeah. So, okay, so now you have something of this kind. Okay, so let's define f of n to be the expected running time of Quicksort, an array of length n. So is the definition of f clear? Because it's a little subtle, right? Because it's the expected running time of the whole procedure on an array of length n. Okay. And so in some sense, what the array is does not matter. Okay, and that's implicitly being used here. Because you're always picking a random element of the array, and the original ordering, for instance, doesn't matter. So that's f of n, and this is already the expected running time. And I would like to write a recurrence for f of n. So yeah, so how do you write? How would you end up with a recurrence for f of n? So you have this array with a bunch of elements. It's unsorted, so maybe a of 0 is here. So on. Now I'm picking a random element and partitioning it into two pieces, recursively sorting. So, can you use this sleek definition of conditional expectation that we saw? So this is, let's call the running time, so that's some random variable. So the running time is, let's call it x. Okay. Now, can you use this nice definition that we saw out here, something of this kind, okay? Right. So what he's saying is, you could define a good event to be, if the first time you chose the pivot, suppose it fell into that interval n by 3 to n by 3. Then you're in good shape. I mean, right? So that would intuitively, you would want that to be your f. Okay. So let me do a pseudo proof, which is not entirely correct, but I will tell you why it's not correct, or I will ask you guys why it's not correct, but based on this idea. Okay, so and in the notes I will actually do the full formula. Okay. So alright, so let's define f to be the event that pivot is n by and 2n. So this is exactly the picture I drew here, right? Like suppose you happen to pick a pivot that falls in this interval. Okay. Then at least intuitively, you have problems of size 2n by 3 and n by 3. Okay. So now you can use this conditional expectation, formula for conditional expectation. To say that f of n equals probability that event f occurs. What is the probability that f occurs? It's 1/3 because we want it to be in this middle third. So it's 1/3 times. And once this occurs, you end up with the split that is something like 2n by 3 plus f of n by 3. That's when this occurs. And when this does not occur, which happens with 2/3, in this case you have something like f of n minus 1. Because in this case, let's assume the worst case, and you assume that you just split it as in the most uneven way possible. Okay? And as you can see, this is where I am lying a little bit, right? So this is not a formal expression because I am intuitively assuming that when we are in this case, this is the worst possible sum. And when we are in this case, when f doesn't happen, this is the worst possible rank. Okay. This, even though this happens to be correct, in general you have to be more precise. And then you have a plus n which comes because the algorithm also has this extra step of concatenating all the sorted. Okay. So, but for now, let's consider this as the recurrence, right? So you have something of this kind. Okay. You guys see intuitively why something like this holds? Right? At least if you assume that this is the worst case, then the probability a third, your split is fairly good, and which means that it's something like 2n by 3 and n by 3. And otherwise your split can be totally off, you don't have any guarantees, so you assume that it's just something like that. Okay. And then you have the n combination. So if this were the recurrence, then you would actually be in decent shape. Okay, so let's see how this is fine. Okay, so if you had f of n equals 1/3 of f of 2n by 2 plus f of n by 2. Let's say you even had 2/3 of f of n. Okay. Not even n minus 1, and you had plus n. Now this looks very much, it should remind you of this probability calculation we did with the coin tosses, right? You can take that 2/3 f of n to the other side, then it would just be 1/3 f of n equals something like this. So then this would simplify to f of n equals f of 2n by 3 plus f of n by 2 plus 3n. This is just algebra, just rearrange. Okay, I've not done anything else. And this one, if you use Akrabasi or something like that, or guess and check, okay. So by induction, you can show this is this f of n is at most c n1. Okay. So at least this is the main intuition for why Quicksort runs in log n time. So assuming that this kind of a recurrence holds, does everyone agree that anyone not sure about why that would imply something like this? Because all I did is just some manipulation, and I'm using the fact that these are all. The nice thing, if you think about it a little bit, is that we started off with trying to analyze randomized algorithms whose running time can vary with time and so on. So, and we're not writing a recurrence for the running time, we're writing a recurrence for the expected running. Okay. And that is this quantity f of n. And the recurrence looks something like that. Okay. So that's what's going on. Alright, and but as I said, here there is an assumption that okay, this is the worst case if your split was even, and if your but in practice it could be. I mean, in reality, if you had picked somebody somewhere in the middle, it would actually be f of n by 2 plus f of n by 2, and it would be nice if you knew that this was only bigger than this. Okay? Then you can say that you can upper bound it like this. But you don't know this for a fact. I mean, you know that this is bigger than this, but that is actually smaller than that. Okay, so you've got to have a nicer way to compare at this point. Yeah.
The problem is actually less than or equal to
Say that again.
the problem is not equal. It is less than or equal to that because you have written worst case in both of them.
Right, yeah. So this is an intuitive worst case that I have written, right? That this is the most lopsided and that is the most lopsided. So you have to formally argue that most lopsided is the worst. Okay. So while it is intuitively kind of clear that most lopsided is
we can use inequality for all the rest and get the
right. So you have to argue that this condition, that this term is actually less than or equal to this. Okay, which so in this case you can, if you guessed that f was c n log n, because n log n happens to be convex, sorry, and that's why you get something like that.
You said people use Quicksort nowadays. Why people use that? Because the running time is exactly the same as the merge.
Yeah. So his question is, why do people use Quicksort given that the running time is the same as that of merge sort? So maybe people know better answers than me for this question, because one reason people always say is it's easier to implement, because there's no merge procedure where you like access two arrays and doing something like this. This is a reason people give, this is what I've heard, but yeah, one could argue it's not that complicated, it's just merging. So another reason people give is that this is easier if you're sorting in place. But I'm curious to hear what others, if others have,
Reference space complexity.
So that's what I meant, like when I said sorting in place, so you don't need extra space, you can do things easily without using additional space. So that's another thing I've heard. But yeah, systems people should probably know these kind of concerns better than me. So from my point of view, all are equivalent.
I see the space is not problem because in the best case you use a middle one. So the best case here is a merge sort that is implemented in the
No. By space I meant like the additional amount of space you use. So imagine here you can come up with these things instead of creating a new array B. Okay, so like you can imagine that you can get this kind of a structure in A by just figuring out the right position for A of I, okay, and then just moving things that were less than A of I to the left and moving things that were more than A of I to the right or something like that, and then you do everything in place. And I think that is easy to do for Quicksort. That's one of the standard reasons people give. You don't have to create new arrays, even though the way I wrote it is create new arrays. But I think you can do it easily without this. Yeah, so there's, I think, some systems reasons for why Quicksort is preferred as the Unix default. Okay, yeah. All right, good. So that's a good question. So, all right. So, yeah, so is everyone clear on this notion that here I have not been exactly formal? Like we actually have to be a bit more careful than this. And there's an easy way to be more careful, which is that instead of using this conditional expectation naively, you can actually be a bit more careful. Okay, so you can say that expected running time of x is equal to, instead of just saying, oh, does the pivot lie between n by 3 to n by 3 or outside, you can be more fine-grained, right? You can say, what is the probability that the pivot is the first element times whatever the running time is for that, plus what is the probability that the pivot is the second element, plus so on. And so that's what we're going to do. So here, right, prob first, or rather smallest. And if you have this, then you have the expectation over x, given that pivot is a small element. Plus probability that pivot is second smallest plus pivot is the third smallest, and so on. So it turns out that this law of conditional expectation, you can do it not just with like f and its complement, but you could have any set of events that cover the whole space. And you can actually say what is the probability of the first thing times the expected value of x conditioned on the first event, plus probability that it's the second event times expectation conditioned on the second event, plus so on. Okay. So you can do this exact same thing, and in this case you end up with something where this is, for us, everything is 1 by n in this case, because you have equal probability of choosing any of these elements. So this would just be 1 by n. So this I'm writing an expectation for f. So this would be 1 by n times, the first term would be something like f of n minus 1 because if the pivot was the smallest element, then you have to only recurse once, and that is into an array of size n minus 1. And if the pivot was 2, you had to recurse into 2 arrays. One was n minus 2 plus f of 1 plus something like f of 3 to the power of 2 plus 1. And you always have a plus n outside. So again, as I was saying, I won't go too much into the details of this. The idea is that, okay, so I'm just expanding out, writing out the algebraic, just the definition, following that idea. Okay, so, and yeah, so you end up with a more complicated summation that looks like this. Okay, and if you simplify it, you end up with some equation that looks like sum over I 1 by n, sum over I going from 1 to n minus 1 of f of I plus f of n minus 1. Something like that. And then you have plus n. So you end up with something like this. Okay. So, alright. And this again, you can do some kind of a plug-in check to see that. Sorry, just guess and prove kind of a thing to show that this is also less than or equal to Cn. But it's not terribly important that you understand how this goes. Okay, so this is just straightforward algebra that is not really algorithmically very nice. But what you should understand is that that's what we did there, okay, to write out the expression. Okay. We said that instead of just viewing it as f occurs or f does not occur, we are doing a more fine-grained thing. We are saying that the pivot could be one of these elements, okay. And then we are saying what is the expected running time given that the pivot is this element, what is the expected running time given that the pivot is this element, and so on. And we are adding those up. Yeah.
But this here after this one.
After the what? Sorry.
In the second row, after.
Oh. So it is just probability that x is that the pivot is the.
No, not. I mean the third one.
Yeah. So this is probability that pivot is the third smallest times expected value of x given that pivot is the third smallest. Next would be the fourth and so on. Okay. Yeah.
Back to this slide. So, no.
Oh, the middle. Okay.
So, yeah, what happened to the components in the extracted formula?
Sorry,
Oh,
just I just did something. Yeah. All right. So, any questions on this? Anyone unhappy with the first statement still? Because if you really want, I can say why this is a generalization of that F statement. Yeah. All right. So anyway, you'll find more details on this once the notes come up. Yeah. So that's about this. All right. So yeah. So let's skip this thing of actually solving this recurrence because we saw the informal recurrence. All right. So now the point is that what I've shown here as a result of this computation is that you could write out a recurrence. Yeah, okay. You could write out a recurrence for just this expected value of the running time on an array of size n, and in this case that is at most n log. Okay, and it's something like c times n log. Yeah.
I'm assuming the more complicated recurrence comes out to C of n log n as well.
Yes. Yeah, so this also comes to exactly c n log n. It will have a slightly better constant than the previous one because you're not assuming that there's some chance that you actually get a little bit better than n by 3 to n by 3. So you get a little bit better than that. Yeah, but it's roughly the same. Okay. All right. So. Okay, so what we've shown is that, have shown so far, that in expectation, something which is at most c times n log n for some constant c. Okay, so some c equals 4. Yeah?
We had to come up with the second expression only because we could not do that n by 3 plus 2 n minus 3 is the best case and n minus 1.
Yes. So the reason, at least the way I stated it, yes. So we did not know a priori that that fn by 2 plus fn by 2 is actually smaller than f of 2n by 3 plus f of n by 2. But actually, as you will read in the, I mean, you can see in the notes, or you can even search for Quicksort. This is actually fairly easy to see. N log n turns out to be a convex function, so it looks. So if you have any convex function, it looks like this because n is a straight line. Think of it. If n is like a straight line, n squared is like a very nice parabola. N log n is something in between, but it's still convex. Okay, so it's something like this. And so if you look at the average point here, it is actually more than this thing. Okay, so and this tells you that so this is n by 3, this is 2n by 3, let's say, and this is the midpoint is n by 2. Okay. So 2 times f of n by 2 turns out to be smaller than f of n by 3 plus f of 2n because of for these kind of functions. Okay. So that's the reason this inequality always holds, okay, for something like but it's not a priori obvious that that is true. Okay. So
So the interval can be anything, right? We are not restricted to be 1 divided by 3. It can be even.
You could do anything. You'll get worse constants depending on. All right. So so that's good. So what we've shown is that in expectation, quicksort an array of length n takes time, which is at most 4 n log n. And the next question we would like to ask is, okay, so the expected value is small. What does it mean, right? So is it that I'm guaranteed that the running time is always small? And that's what we'll see next time. So it's by turns out that you get an easy guarantee of this kind, a weak guarantee of this kind pretty easily in general. Okay, so that's called Markov inequality. So we'll see that next time. I wanted to leave some time for filling out that short survey. If you have time, you can hang out here and do it. Otherwise, you can go back. I think we're almost out.